Hi, hello, and welcome to section number 8. Woot, woot, only 2 sections left. Gasp. Tears fell across every face in the audience. Really unfortunate. I've been having mid-semester check-in meetings with people so far, which have been lovely. If you have not signed up for one, sign up for one. There are still more slots. They're going to be in the Smith Campus Center near the Mother Juice, right off of like Holyoke Street. Why do you have Monopoly?
Because I have like a study break later, so I had to pick it up on my way here.
Ding dong. Ding dong. Thank you for filling out the mid-semester feedback. I'm still kind of working through all of it. Y'all were very nice. The suggestions are kind of like feedback things to improve upon or change. One of them was about like posting the section video, which the files are just really large. And so if I'm going out of town Friday through Sunday, then it doesn't get posted till Monday. But that's why I have all the 2024 videos posted. And so if you ever need to watch a video and it's not yet posted, the 2024 one will get you there, you know? So that was one. And then for other kind of feedback that students had, it's so hard because people said exact opposite things. Some people were like, we need more time in section to attempt the problems on our own before going over them. And then other people were like, giving us time is a waste of section time. We should only do guided problems where we're like seeing it worked and we don't struggle with it on our own. And so like it's kind of like balancing all of them out there. I'm just like, we'll strike a balance. We'll try. And then also ones where like some people are like, I wish we were doing harder problems in section because like we do a lot of foundational ones to kind of pick up the pieces from lecture, hopefully to set you up to do the challenge problem ones like that are harder. And then sometimes when we do a full challenge problem, like a synthesis for the last 15 or 20 minutes, students in the feedback said, doing the hard problems at the end just, it doesn't work. You know, at that point I'm just writing things down, I'm checked out. And so I'm like, I don't know what to do, but we'll try to strike a balance of it, and yeah, maybe I'll do more like calculations of the survey and see if like there was a clear winner of things. Y'all seem to like the section notes, which I'm so glad, and I'm so glad that they are helpful, because the one critique of them is they certainly are busy. They are certainly a maximalist approach, but I'm glad that they've been helpful with studying. So thank y'all for doing all of that. Game plan for today. So we are going to talk about some alkenes. And really, I'm going to divide it up into kind of some simple alkene reactions. And then I'm going to talk about a few of the kind of complex alkene reactions. And then at the very end, leave off with the Wittig reaction. Radicals, which y'all started at the end of lecture 8, I'm going to cover in section 9. So that will be the first topic of section 9. But just to show the overview, we finally made it to my favorite thing that I've made in this class, which is my little reaction web of all the alkene reactions. Like there's a color ombre, the colors sort them into reaction families based on similar mechanisms. It has like details on all the mechanisms and like all the key features on the outside. On the inside is all the reagents. Then we have the analysis of like the 3 logistic questions all around those. So many things. Anyone want to guess how long this took? 2 weeks? Give me hours. Oh no, it's not that bad. That's crazy. That's really crazy.
10 hours.
I would say typesetting this one probably took like 12 to 14. Yeah. And this one, I think this draft came in 2023. And then I made like small tweaks after that. Before that, I had a version, but it was just a little bit less calcified. But yeah, no, it's a pain in the butt to make, but I do fear she slayed, Your Honor. Yeah. So one thing I want to do to talk about this whole family of reactions, because there's a lot, is I feel like we need to figure out ways of breaking it up. Because if we think of this as one big reaction family, then it's just a little overwhelming. So where I kind of make some divisions are right here. It's a little bit, it's not exactly center, but to the right of it, these families with the red, the purple, and the blue, these are the ones that I call the simple alkene additions. So these are ones where the mechanism is pretty heavily tested and where we want you to know like all the details, all the ins and outs really thoroughly. And we'll ask you kind of trickier things about the specific mechanism. Whereas on the left side over here, if the right is simple, left I call complex alkene additions. These are the ones where sometimes we're like, don't learn the mechanism. These are a little bit more complicated, weirder reagents. And the complex ones primarily are tested based on line reactions in synthesis. They're not really as tested on like mechanism things. And so it's just a different kind of approach here. So we're going to be doing some detailed work today with the simple reactions and then just hitting some high points for the complex ones. Cool. Any like logistical questions before we jump into section at large? So alkene reactions. Each alkene reaction that we teach you in this course, there are essentially 3 logistic questions that you need to know the answers to for the reaction that we taught you. So the questions are what, where, and how. The what is what 2 groups are added to the alkene. So anytime you're doing an alkene addition reaction, you're adding 2 things, 1 to each carbon that was in the double bond. And so when I write like H3O plus as the reagent for the alkene, I need to know that that adds an OH and an H. If I do like Br2, what 2 things do you think are added? Br and Br, yeah. And so just for the reagents, then it gets a little bit harder when you do OSO4 and HSO3. What 2 things are added? Well, 2 OHs. And like that's the thing where you have to know it for the complicated ones as well. So what is added is the first part. Second one is where. That's our regiochemistry question. And the answer to where are the groups added, the 2 things, is typically Markovnikov's rule. So our version for our class of Markovnikov's rule is that the more electronegative group adds to the more substituted side. You might see it written differently in other classes. They might do like the hydrogen adds to the less substituted side, which most of them are pretty equivalent. But ours, I think, is a little bit more like comprehensive. Now, the more electronegative group is typically your nucleophile for the reaction, and the less electronegative group is typically a hydrogen. So when I say like substituted side, carbon 1 or carbon 2, which one's the more substituted side of the alkene? 1, and it's because it has more carbons on it other than just hydrogens. 2 is unsubstituted, it only has hydrogens on it. So in our Markovnikov product, our nucleophile, the more electronegative one, adds to the more substituted side. And then our hydrogen, or whatever is less electronegative, adds to the other side. If we want specifically to do the opposite of that, we want to add our nucleophile, more electronegative thing to the less substituted side, then the regiochemistry we want is the anti-Markovnikov product. So for each reaction, you'll have to know whether it's a Markovnikov or anti-Markovnikov. And when I go around the circle, it's very duck, duck, deuce. Like Markovnikov, mark, 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 mark. Anti-mark, run. Like you only are going to learn like 2 that are anti-Markovnikov. So most of them are Markovnikov. Now there are some that I put, quote, Markovnikov. Well, these are ones where we're adding 2 of the same thing. So is there a more substituted version? No, like they're equally substituted. So it doesn't really apply, but just to make things easier, we say Markovnikov. Then our last question is how. So when we add our 2 groups, our double bond, imagine it's just kind of like this right here. When 2 things come along, they could both add on the same side, either top same side or bottom same side, which is syn, or they could add on opposite sides, like one adds up, one adds down, and vice versa, and that would be anti. And we can see that like with wedges and dashes here. So here these are syn because they're both on wedges or both on dashes. These are anti because they're mixed. Or you can think about it more in this kind of like 3D way. So I tried to draw it several different ways. We also have a dance that we're going to do. So the dance is syn, syn, anti, anti. Can we do it? 1, 2, ready, go. Syn, syn, anti, anti. Like, do you know the meme of the Camp Rock? Dun, dun, and then they do a little Camp Rock, and then they're like marching through the forest. That's what I want you all to be doing. Like, see each other in the wild, walking through Harvard Yard, and you'll go, Yeah, like really make it seem like a cult. Really make people wonder about you. So that's our sin and anti. And one thing to notice is anti-stereochemistry is different from anti-Markovnikov. They just have the same letters. So watch out for her. Do not mean the same thing. Anti-Markovnikov is about the regiochemistry, where things are added. And then anti-stereochemistry is about how it's added on the wedges or dashes. The other thing is some reactions don't have a preference for sin or anti, in which case we say they're mixed. So someone suggested in the 8 a.m. we do sin, anti, mixed, or something. But live your truth. I'm not convinced on that, so if someone has a better suggestion for how to incorporate mixed, let me know. You can be our dance captain. So now, all of this like sin and anti, wedges and dashes, it's a little stressful and it makes problems harder, but it's only applicable some of the times. So if we look at this reaction, this alkene making this product, we've added R1 and R2, some groups. Is that a stereocenter? No, 2 methyls. Is that a stereocenter? No, 2 hydrogens. So we don't have any stereocenters. We don't have to worry about sin or anti or whatever. Like, yeah. The thing that it just reminded me of is like there used to be this like LGBT like community organization called GLOW, gay, lesbian, or whatever. And so this is like sin, anti, or whatever. Like we don't care. It doesn't have stereochemistry. But these are our kind of 3 main questions. And what I've tried to do in this web is the what, where, and how are all in the like little like space right outside the bubble for all of them. So I've already done that kind of analysis work for y'all to make it really clear just to see those patterns. So any questions about our terminology here before we jump in? Okay. Let's begin. So the first family of our simple alkene additions are acid additions. They take place in some sort of acid, be it could be HCl or HBr, or we can think about it as an H plus with water or an alcohol. Any of them work. But the first step is the same for all of them, in that the alkene goes and grabs a proton. So it grabs a hydrogen. When we do that, we have 2 options for where our hydrogen could add. It could add at this left side here, or it could add at the right side here. And to know which one happens, we have to look at the carbocations. So here, which carbocation is more stable, the first one or the second one? The first one, because it's more substituted. So we form the carbocation on this left side, we add the hydrogen on the right side. And I will grant that this, I need to edit this. I've left off a methyl for this, so it doesn't match up exactly with this problem, but it's still the same idea that we form the more stable carbocation. And then at this point, whatever else is in the reaction mixture comes and attacks. So like if you are in HCl, a Cl comes and attacks. If you are in HBr, a Br comes and attacks. If you're in water, a water comes and attacks, so on and so forth. So something comes and attacks, and then you've added your second group. Now, this one, the hardest thing about the acid additions are kind of twofold. First of them, you are forming carbocations, so she could rearrange. So watch out for her. I would say anytime you're doing an acid addition, draw the carbocation just to do that checking both ways before you continue in the reaction. You want to make sure that if there is an easy rearrangement that you clock that, and that's not 2 points missed on a test unnecessarily, you know? So be careful to watch out for rearrangements. The other hard thing about these acid additions have to do with the stereochemistry. So do y'all remember deuterium? Deuterium is just the isotope of hydrogen. It's heavy hydrogen. What we do here is, first step, we are going to add a hydrogen, and we want to form the more stable carbocation. So is the carbocation up top or below more stable? Or are they equally stable? And just as remember, deuterium is like a hydrogen, not a carbon. So if I just kind of erase this so you could treat it like you would do to a hydrogen where it's implied, This one's tertiary. This one's secondary. Which one's more stable? Tertiary. So the hydrogen is definitely going to add on this bottom carbon, and we're going to make them more stable tertiary carbocation at the top. But already, we can think about, if our double bond's here, we could grab the proton from above, in which case it's added on a dash, or sorry, in which case the H is added on a wedge up top, if the acid comes in from the top face. Or it could add it from below, if the acid comes from below the alkane. So it could add on a dash. So already we have two options. But then, here, when we have a carbocation, we talked about this with SN1, we have an empty p orbital, right? And so our nucleophile could attack from the top face, or it could attack from the bottom face. So you get two options for each of these. You get a total of 4 products. Gross. I'm so sorry. So like here, it's helpful to remember our enantiomer, diastereomer terms, where when we say some but not all of them swap, and we say that they are diastereomers, when we say that all of the wedges and dashes swap, we say that they are enantiomers. So if we asked you to draw the products of this reaction with stereochemistry, you would need to draw 4 things, which sucks. But there's a shortcut way that you can do it. So the shortcut way that you can do it is just draw one of each version here, the one where they're both the same syn and one where they're opposite anti. And then for each one of these, put a plus minus. When you put a plus minus like this, it's saying, hey, we have this version where they're both on dashes, and we also have the version where they're both on wedges. So it's essentially a way of writing all 4 products, but only having to draw 2 structures. So that is something to watch out for. Yeah, and then also, this reaction, because you have that carbocation, it can add at either face, we get the mixture of syn and anti. We don't get just syn or just anti as our product. So because there are lots of possibilities, that's what makes this one a little bit challenging. At the bottom of this, I've just put the 4 main players in this family, and each of them are adding a hydrogen because we are an acid addition. And then the second thing that's added is either a Br, a Cl, an OR, or an OH.
And these all produce like the 4?
If they have 2 stereocenters formed. So like, the thing is, if this was a hydrogen instead of a deuterium, then we would have hydrogens here, right? So these aren't going to be different options. They're just going to be one stereocenter. And if there's one stereocenter, then there are 2 products. If there are 2 stereocenters, there are 4 products. I know it's a lot. But with this, I'd like you to try out some of the stereochemistry here. So let's go to practice number 1 here. These are some problems that I made. And I want you to try to draw all the products formed. As a first step, I'd like you to draw what the carbocation looks like just to check for rearrangements, and then try drawing the products in there. Let's talk about it. So, here we are. First one, make our carbocation. We want the carbocation to be on the more stable side here. So the tertiary versus if we put it over here, it'd be secondary. So for this, is this carbocation going to rearrange? It's next to a quaternary carbon. But is she going to rearrange? No. And it's because she's already tertiary. So she's not going to become more stable if a rearrangement happens. So we're good. No rearrangement. But then with this, now this carbon right here, is it a stereocenter? No, because we already had one hydrogen on it. Now we have two. No stereocenter. So we are only going to have two products here where essentially it's our water either attacking from the top face or the bottom face. So just as a reminder, H3O plus adds an OH and an H. We added the H in the first step. So now over here, drawing our products, I will draw just one of the versions. So this is the version where the H2O attacked the bottom lobe, and so now it's on a dash here. And to indicate that both are formed, I just put my plus minus to indicate that we have the enantiomer as well. On the second one over here, we make our carbocation on the right, and so we add our hydrogen on the left. And then is this a stereocenter? Yeah, we're attached to a deuterium, a hydrogen, an ethyl, and then something else. So this forms a stereocenter, then this one, when we attack it, will form another one. So we're going to get 4 total products. Great, I hate it. So there are a few different ways that you can write it. The way that I would do it, actually, to be so honest, the way that I would do it is kind of mindless. So it literally is just make sure you get all of the options. So HCl adds an H and a Cl. We know that this carbon is going to need to have a methyl and a Cl on it. So I'm just going to pick one. So let's put the Cl on a dash. So in this one that I've drawn, I have put the H that I added and the Cl that I added syn or anti to each other? Syn. So I need, in the other one, to draw the anti version. And you can draw it whichever way you want, but just draw one of the anti versions. So I'm going to keep this side exactly the same. And then I'm going to now make sure the Cl is anti to the hydrogen on the other one. So now we have the anti version drawn. And to make sure that we have all 4 of our products formed, I'm going to put a plus minus with each of these. And that's going to get us all of our combinations of wedge, wedge, dash, dash, wedge, dash, dash, wedge. As long as you know you're forming all of them, you don't even have to think through all the minutia details of like which one forms from which version. Just make sure you get all 4. Yep.
For the first one, does it matter which carbon you want to make a wedge?
Like between putting this on a wedge or putting this on a wedge?
Or I'm saying the other, like the methyl or the, what does that mean?
Oh, wait, sorry, for this carbon? Or
No,
for
I'm talking about for the first question. Like.
Oh, this. Like,
Yeah.
whether we put this in the plane and this on a wedge or vice versa? No, it doesn't matter. Tell your truth. Yeah. Cool. So that's kind of the stereochemistry. That's the only really complicated thing with our, like, basic little anti-additions. So, moving right along.
Yeah. Oh, yeah.
The halogen anti-additions. So, just based on the name that I gave this family, do you think that this is syn or anti? Anti. Yes. So, the mechanism here is fundamentally very different from the carbocation thing, the grabbing the acid. So, these reactions always happen with a dihalide. And what happens is the pi CC of the alkene is going to attack the sigma star dihalide bond. Now, when we do that attack, we're putting electrons into an antibond, and so we have to break that bond. This is kind of a consequence arrow. The thing that's weird about this is at the same time that we're doing this, this halogen that's like, you're going to attack me, I'm going to attack you right back. And so we have another interaction, which is a lone pair on the halogen attacks the pi star CC, which breaks the pi bond, and those electrons are going and attacking. It's a concerted mechanism. Concerted. It all happens at once. So when we do that, we are making two bonds with this halogen. And so it forms a little cyclic three-membered ring. And if we have a bromine here, we call it a cyclic bromonium ion. If we have a chlorine, cyclic chloronium ion. And now, again, depending on which face of the molecule we reacted at, we'll get two options. So if our alkene was here and our molecule came from above, we have an up triangle on wedges. If it came from below, down triangle on dashes. So already we're in kind of all the different enantiomers mode. But then, remember, this is very similar to a protonated epoxide here. So let's go back and look at our epoxide diagram to think about how this is going to attack and become anti. So here, when we have the epoxide going up, and now we can imagine this is our Br plus going up, we know that when we attack this, we have to attack the antibonds, which are going to be below the ring. And so when our nucleophile attacks, it's going to be coming from below, whereas our Br we added initially is above the plane. That's how we get our anti-orientation, because our nucleophile is attacking from below, and then our Br that we add in the first step is above. And vice versa. If we had the version where you had the Br below, then the antibonding orbitals would be above, and so the nucleophile would have to attack from above, and then you would have anti-orientation yet again. So that is why we only get anti-products for this. The other thing, regiochemistry, where does it add? Well, our nucleophile is going to attack the more substituted side, just like in the acid version of epoxides. So the base version of this is Br2 or Cl2, in which case the things that you add are just two Brs or two Cls. Easy enough. But then if you have this dihalide and water, you get a scenario like this, where you've made your cyclic bromonium. Who do you think will attack first? One bromo boy or any one of the millions of waters? Water. It's not that water's a better nucleophile, it's just it outnumbers. So it is going to come and attack and then kick it off. And then we'll have a deprotonation step, but at the end of the day, that H2O that attacks is going to be turned into just an OH. So the two things that these reagents will add is a Br in the first step, and then OH. Same thing over here, Cl and OH. The last one is, imagine all of these were alcohols, ROH, 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 instead of water. Who do you think wins? One bromo boy or one of the many alcohols? The alcohols. And so at the end of the day, what gets added is one of the halogen and then an OR group. And so, another way of making ethers. I'm so glad I know so many ways of making best functional group. I hate ethers. So now with these, kind of like epoxides, you get functional groups on two adjacent carbons, which is interesting and something to kind of keep an eye out for. So they have special names. Like here, if you have two halogens next door, they're called vicinal dihalides. Vicinal because they're in the same vicinity. Here, if you have an OH and a Br added, it's a halohydrin, which, where did we see those before? Yeah, they are the functional group that if we add NaOH can form an epoxide. So now we know how to make halohydrins. Great. And then this, where we have a halogen and an ether next door, haloether. So with this, what I'd like you to do is I'd like you to try out this skill builder. So this does not use an Br2 or I2. It uses a mixed dihalide where we have an iodine and a chlorine. And a note here is that chlorine's more electronegative than iodine, but I'm also going to give you a hint. For an antibond, a sigma star, which lobe is larger? Or the larger lobe is on which element? That's a better way to put it. Gosh, I just don't want to write all that. The larger lobe is on which element? So I will let you try it out, and then also because this is a pretty quick one, I'm also going to do another like bonus question. So try it out. Let's talk about it. So, for antibonding orbitals, is the larger lobe on the more or less electronegative element? Less. So, what we're going to have is in our sigma bond here, it's normally on the more electronegative element. So, it's going to be kind of lopsided, where a sigma bond here, it's more towards the chlorine, more electronegative. But our antibonding orbital, it's going to be larger here and smaller here. So, our bigger target is on the iodine. So what's going to happen is our double bond will go and attack the iodine, and then we will break it off. And then remember, our halogen, it attacks right back. So it is going to circle back and attack the alkene, the pi star CC. So when we have that, we are going to make a 3-member ring with an iodine. And if we had cyclic bromonium, cyclic chloronium, anyone take a stab at what this one's called? So close. Cyclic iodonium. Ooh, ooh. There is an extra little D in there, so that's fun. And then we have a Cl minus left in the mixture. Is it going to attack the more or less substituted side? the more, because it's like the acid conditions for the epoxide, it's attacking the side that has a partial positive more stabilized. And then we are going to kick this off. So what we get is an iodine on the right, a chlorine on the left. And then what's our stereochemistry situation? Do we have any stereocenters? No, so easy. One product. Love to see it. So for this other one, our Br2 reacts with the alkene, makes a cyclic bromonium. Oh, I need my plus. But then, what do you think is going to happen? Do you think our one bromo boy is going to go and do the attack, or something else? We have this, right? We have an alcohol. And remember, if we had, like, imagine we didn't have this and we just had, like, MEOH, then in the step 2, the alcohol would go and attack, right? Now we have that, but our alcohol is just on the molecule. And intramolecular reactions are super, super fast. So before the bromine can come around and do a backside attack, this oxygen lone pair is going to go and attack. And now, does it attack carbon 1 or carbon 2? Carbon 1, it's going to attack the more substituted side, exactly like we've seen in all the other anti-additions here. And when that happens, it's going to make a 1, 2, 3, 4, 5-membered ring, with oxygen as one of the 5. 1, 2, 3, 4, 5. And then carbon 1 is going to have a dangly bit and a bromine. Like this. 5, technically, if we just do the full mechanism, it's going to be OH plus, and then we're going to deprotonate it. So I'm just right now going to draw the product of it because I think that y'all can do deprotonations just fine. But stereochemistry-wise, what do we have here? Is this a stereocenter? Is this a stereocenter? Yeah, it is. It has this, it has a hydrogen, it has the ring with O and the ring with carbon. So 4 different things. We're going to get both versions here. We're going to get the wedge version and the dash version. So just draw 1 and then do the plus minus to indicate you have the enantiomer as well. So that's kind of the extent of the challenges for the anti-additions like this. It's just making sure your products are anti, and then we can add some kind of more, conceptual versions of this. So I'm going to plow right ahead and get to the last family in the basics. So, what's a good transition? So, alcohols. Essentially, what we want to do is we want to control the way that we could turn an alkene into an alcohol. Because right now, the only method that we've talked about is H3O+, and H3O+, wild and wacky rearrangements, carbocations. So here, it'll have this methyl shifting. What if we just want to do Markovnikov addition, and we don't want a rearrangement to occur? We need another girl to do this. So this is our oxymercurinium, or oxymercuration reduction. Oxymercurinium is the intermediate. So HgOAC2 with H2O, and then second step, NaBH4 for our reduction. So that is going to give us our Markovnikov with no rearrangement. And the last type that we want to try to do is if we wanted to add our OH to the other side, then what we are looking for here is our anti-Markovnikov product. So for this, we use hydroboration oxidation. That's going to be BH3, THF, H2O2, OH minus. So now, for this, let's talk a little bit about these other 2 flavors and why they do the no rearrangement and why they do the anti-Markovnikov. So oxymercuration reduction, HgOAC2, it's really going to function a lot like our halogen anti-additions here, where the pi CC is going to attack the sigma star HgO. That's going to cause this bond to break because we're putting electrons in the antibond, and then the mercury is going to attack right back. So lone pair on Hg, attacks the pi star CC. When we do that, we get our cyclic mercurinium ion. So cute. And then this, again, like the epoxide and acid, like the anti-addition, we're going to have some nucleophile come and attack on the more substituted side. Now, if we do this with H2OAC2 and water, water is going to be the thing that attacks, and that's eventually going to make an OH here. So that's how we get the alcohol added that we want. But we could also do this in alcohol instead, in which case an HOR is going to be the one that attacks, and then in the product you would have an OR group added. There is a deprotonation here that, again, I'm leaving out just to make it look nicer. But yet again, another sneaky way of making ethers. I hate it. So we do our attack, and we have an anti-orientation where we have this HGOAC on our molecule, and then we have our OH, or we have our OR. Now I don't like her. She's an organomercury compound. Organomercury, that's like the scary story in the lab safety video where like the scientists got one drop on their skin and they knew they were cooked. Within 10 days she was dead, and she like realized like the toxin was getting in her brain, and she felt her brain stop. It's like scary stuff. So will y'all ever do oxymercuration reduction? No. Would I? I would never, me personally. But yeah, so she's yikes. And then we have to remove her, and we remove her with NABH4. I know y'all have seen NABH4, but this is NABH4 like you've never seen her before. She does like radical things, and you are not responsible for it. So all she does is says, let me shake it up. Let me scramble it off. And when it removes this HGOAC, this is Logan's little fake mechanism of just erase everything. When it does this, it scrambles the stereochemistry. So essentially, this is where you do need to know a little detail. You can't just always erase if you're having to do stereochemistry, which is that like this bond is going to break and it's going to do radical stuff, and then the hydrogen that's added could add on a wedge or it could add on a dash. So if you have a stereocenter here, you're going to get both options. You'll get 4 products again. 9 times out of 10, this reaction, it's not going to have a stereocenter here. Like one of these things is going to be a hydrogen, and so you don't need to worry about it. But I just want to show you the most complicated version so that you are prepared. Work. The other one is hydroboration oxidation, where essentially the way it works to get our anti-Markovnikov product. So see here, we have our OH, the more electronegative thing, added to our less substituted side. So that seems to be like a violation of our Markovnikov rule. But essentially, we just do a little trick. So step 1, we have BH3, and the pi CC is going to attack the 2p boron orbital, empty p orbital. And then instead of a lone pair attacking back, we're going to have a sigma BH bond attack the pi star CC. Kind of like the NABH4 things, where you've seen a sigma bond attack that way. Now, when you do this, between boron and hydrogen is actually going to be the more electronegative one. So boron has electronegativity of 2.04, hydrogen's 2.22. So Markovnikov's rule says more electronegative adds to the more substituted side. So did we follow Markovnikov's rule? We did. We did. But then our second step, which you are not responsible for the mechanism, what it does is it replaces the BH2 with an OH. And this one doesn't scramble the stereochemistry. It stays like with this syn orientation here. And now when we do this, if you didn't know the mechanism, if you just looked at the product, does this look like Markovnikov or anti-Markovnikov? It looks like anti-Markovnikov. We've added the more substituted thing on the less substituted side. So it's kind of like a trick of the mind. Like it follows all the rules here for like Markovnikov's rule at this key point where it reacts with the alkene, and then later we just replace it. And so that's how we get overall an anti-Markovnikov reaction. The other thing with this one is, remember the first step in mercury is going to be anti-addition because we form our cyclic mercurinium ion. It's like the halide anti-additions. But here, if our double bond's right here, BH3 drifts in from above, both the hydrogen and the BH2 add on the same side because that's where the molecule added. Or if it came from below, they would both happen at the same time below. And that's why it's going to be sin. Now, I have some like facts here. Like these are just truly FYI if you're interested. If you are not interested, block it out. These are just some other things. Like if you wanted to see the oxidation mechanism, she's kind of cool. I don't know. But now I'm going to tell you something that's going to make you lose like 15 points on your estimation of my IQ. Like it's really going to make it drop here. It's very embarrassing. So ways of remembering this. The way I think about if we want no rearrangement is like praying, please let there be no rearrangement, and you've exhausted all the gods. So you have to go back to the Greek and Roman gods and say, Mercury, please make sure there's no rearrangement. And that's how I remember to use HD Mercury to get the no rearrangement Markovnikov. It's really, really, really smooth brain. The hydroboration oxidation's even smoother, so watch out for this. So hydroboration oxidation, HBO. So we can call it HBO reaction. HBO is a streaming platform. What's on a streaming platform? Movies. What's a movie? The movie John Tucker Must Die. The early aughts comedy movie about a guy, John Tucker, who's like cheating on these 4 girls, and then they like put it together and they like get revenge. So in this movie, John Tucker Must Die, that's on HBO, hydroboration oxidation, they're anti-John. If the character instead was named Mark, they'd be anti-Mark. So hydroboration oxidation, HBO, John Tucker Must Die, anti-John, anti-Mark, anti-Markovnikov. That easy. And that's how I remember it. Or you can do the reverse of I want to do anti-Markovnikov, anti-Mark, anti-John, John Tucker Must Die, HBO, hydroboration oxidation. And the crowd was silent. Yeah. So do whatever is going to make it work for you. But I find when it's more ridiculous, it works better. And then someone in the 8 a.m. section Googled it, and apparently this movie is not on HBO. So that's really fun. The other thing I like with calling this HBO is like the uncensored like TV network. And so what's on HBO? Sinful behavior. And what type of stereochemistry is this reaction? SYN, sin. Ding dong, my lonely monarchs. So with that, try out practice number 3 here. So the first one is going to be doing a mechanism for the mercury reduction here. And then the second one is doing hydroboration oxidation, but we do it with deuterium. So think about where an H is going to be versus deuterium. And then the last one is a little part of a challenge problem, a little mini synthesis, where we're going to try to go from this alkene to this alkyl halide. So I will have you try it out. For this top one, technically in the question it doesn't have stereochemistry, so you normally don't have to worry about it, but I have indicated the stereochemistry here just to make it more clear. Welcome back. So, the first one, I've just kind of put the answer up here because it's kind of just straight up regurgitating the arrows. The only things that can be a little bit trickier maybe stereochemistry things. So here, we could have formed this on a wedge, or we could have formed it on a dash. Either one happens, and so we have to have our plus minus here to say that both options were valid. And then, once we do that, this is the step where in the original one over here, like water would attack, but now we have an alcohol instead of water. So MeOH is going to attack, and then we do a deprotonation. Now, when it attacks on the bottom face because that's where the antibond is for this on a wedge. So it's added on a dash here, but remember, still we get a mixture because there was also the version where this was on a dash, in which case the MeOH attacked and it would be on a wedge. So you're going to get both of them. This one over here is not a stereocenter, so we don't have to worry about it. Then, step 2, the NaBH4 just replaces the HGOAC with a hydrogen, so nothing crazy. And it technically scrambles the stereochemistry, but there's not a stereocenter, so it doesn't matter. Second one, with hydroboration, it's very similar to BH3, BD3. It's going to do the same arrows of the pi bond attacks the empty p orbital, the sigma bond attacks back the pi star. And we add our more electronegative, which is in this case the deuterium, which again is like hydrogen, to the more substituted side. But then question, is this a stereocenter? No, because both parts of the ring are equal. So that's not a stereocenter. Is this a stereocenter? No. So we don't have any stereochemistry to worry about. And then the second step replaces our BH2 or BD2 with just an OH. So our product here, we have a deuterium added here from the first step and then an OH from the second step, anti-Markovnikov. Now, over here, if I just look at the synthesis, I'm looking at what two things were added to the double bond. So one of them is definitely a Br. What's the other thing that was added? An H. So I think about my acid additions, but if I just did HBr, then what's going to be the issue with HBr? Well, we'd add the H here, and more than just adding the Markovnikov, we'd have a rearrangement. We'd have a ring expansion. So, yikes. So, she doesn't work. Then, over here, yeah, we see that we want it to be anti-Markovnikov at the end of the day. Well, there is a reaction that you learn in lecture, a radical one, that can do HBr anti-Markovnikov. But for the same reason that the carbocation version doesn't work, the radical version doesn't work. It's going to do a ring expansion, which again, that's more complicated stuff. We're going to address it directly in section 9. But for now, why don't we just use our reliable go-to anti-Markovnikov reaction, which is going to be anti-Mark, anti-John, John Tucker must die, HBO, hydroboration oxidation. So easy. So if we use our BH3 THF, H2O2 OH minus, that is going to give us our anti-Markovnikov addition of an alcohol. And how can we replace an alcohol OH with a bromine? We need to make the alcohol leave. Say again? Oh, okay. Lecture 7, making alcohols leave. Say again? That's going to oxidize the alcohol. They take it to a carbonyl.
Change it to OTS.
That's one way of making alcohols leave, but we want to make it leave and turn into a bromine. So OTS is one in the family. There's one that makes into a chlorine, then one that makes into a bromine. What's the reagents that make into a bromine? PBr3. So again, it's all connected. It's all connected. I kind of liken it, exam 2 is going to be like you've been watching a TV show, and each episode of the TV show focused on a different set of characters. And then exam 2 is the finale of the season where all the characters apparently know each other, and it's like, whoa, like the Not So Sweet Life of Hannah Montana kind of vibes. But much more stressful. Yeah. Cool. So now we're going to move straight from this into practice number 4. which is tricky, which is why I want to do it together. And to be full disclosure, even after going through it, I do think only like half the class is going to get it because it's just a little tricky, and it's also a lot of work for very little payoff. So the other thing I will put right out there is if you don't do this on a test, it's like maximum a 2-point deduction, and it just might be worth the time to take the 2-point deduction. I'm going to show you it, we're going to teach it, but it's just a little difficult. So what we're going to do with each of these reactions is we are going to first ask ourselves the what, where, and how. So this D2 palladium on carbon, we haven't talked about it yet today, but you saw it in lecture. It's kind of like our H2 palladium on carbon. What two things does H2 palladium on carbon add? 2 hydrogens. So D2, what do you think it's going to add? 2 deuteriums. Now, if we have the same thing, Markovnikov or anti-Markovnikov doesn't really make sense, so we're just going to do it's Markovnikov. And then, is this going to be a syn or anti-reaction, which is just one of the facts that we have to memorize of other reactions? Syn. And again, it's because this palladium on carbon is a surface, and so the alkene has to react on the same side of that surface. Okay, so we know this. So if we look at our products, we've added our 2 deuteriums here. So that means our alkene had to be here, right? It had to be between these 2 carbons. But then stereochemistry-wise, our product could be this, or it could be this. So in one of them, these 2 methyls are cis to each other, and one of them, the 2 methyls are trans to each other. And like, truly, this is the thing that to decide which one, we have to do some work, and it's just kind of annoying and takes a long time. And if you just ended up putting the wrong one on the test, it would be a -2 points. Like, it is what it is. But in order to see this, we have to draw these 2 things in a way that looks syn. Do you see how right now one of these is in the page, one of these is dashed? It doesn't look syn, like on the same side. And so one way that you can write 2 things looking syn is having them both be on wedges, both be on dashes. But specifically for this scale, I think it's more helpful to think about them in the plane. So what I want to do is I want to redraw this so that both the deuteriums are down in the plane. So they're syn to each other. Now, for this right carbon over here, that's how it exists already. So we can just leave the wedges and dashes exactly like they are. So here, our methyl is on a dash, and then here we had a hydrogen on a wedge. That's exactly the same. But then over here, we had to do a small little rotation, and it's only a 60-degree rotation. So let me do it like this. Imagine the deuteriums or the blues here. So this one's in the plane, and then this one's going a little bit away from you, but it's down. And then this red is going to be the methyl on that carbon, and it's on a wedge going towards you. So going away from you, dash, wedge towards you. We want to make this deuterium just be in the plane with the other one. So now what happened to our methyl? Is it still going to be going towards you on a wedge? Is this coming towards you? Yeah, so it is. But now it's an up wedge. So it went from being a down wedge coming towards you to a 60-degree rotation up wedge. So the methyl gets shifted up here, and then the ethyl gets rotated back, just with that 60-degree rotation again. So the whole reason why we rewrite it this way is because when we do, it's really clear that these are syn added on the same side. And we can do this fun little trick. So if we have the syn where we can clearly see them on the same side, what I'm going to imagine is the methyls are red here. So one is coming towards you, one's going away from you, right? Verify this looks okay. So what we can do is syn, we can fold this together as if this was our double bond. And now look at our 2 methyls. They are trans to each other on this double bond version. That lines up to, on the paper, the things that are wedges are going to be on the same side of the double bond. They're going to be cis to each other. And the things that are dashes are going to be cis to each other. So that corresponds to, we want the methyl and the H cis, and we want the other methyl and the ethyl cis. And so that's how we get the version that we started with must have been this one where the methyls here were trans to each other. So we definitely started with this product and not that one. Do you see how much work that was just for that? Like, it's really like outsized of how much effort to get it, which is why I'm like, there's no shame in like just piecing out, especially on like a timed test. But I'm going to do another couple examples with y'all to see it and to show it. So we're going to do the same process again. So I2, what two things does it add to an alkene? Two I's. This is, quote, Markovnikov again, just because they're the same. And then is this a syn addition or an anti-addition? Anti. So when we had a syn reaction for this, we want to make sure syn, we are drawing our two things that we added either up or down in the plane. But if it's an anti-reaction, we want to clearly show it's anti, so we want one to be down, one to be up. Either way you do it. So let's draw this with one of the I's up, one of them down. And hey, that's how this molecule already is. We don't have to rotate it, which is really, really nice. So on this one, we have the ethyl on the wedge down, the hydrogen on the dash down, ethyl on the wedge up, hydrogen on the dash up. We clearly have the two things that we added in the anti-orientation. And what we see is the two ethyls are cis to each other, and the two hydrogens are cis to each other. So our alkene that we started with, we place the two ethyls cis and the two hydrogens cis. So we get this version and not this version. So these questions aren't horrible if you don't have to rotate it. But if I'm guaranteeing that there's going to be one of these on the test, and I'm going to guarantee that you have to do some sort of rotation. I can guarantee that because I impact him writing it. But every year there's always one, and you'll see him on the practice test too. Okay, last one here. Hydrogenation oxidation. Which two things does it add to an alkene? Yeah, an OH and an H. Then, is it Markovnikov or anti-Markovnikov? Yeah. Which, the only way you could have known that if you thought hydrogenation oxidation, HBO, John Tucker must die, anti-John, anti-Mark, obviously. And then, is it a syn or an anti reaction? Syn, in terms of the stereochemistry. So, with the OH and H, we could have had this H over here be the one that we're talking about, or it could be this one over here, right? So between these two, how do we decide? Well, if we did this, like if our alkene was this one and we had an OH and H, do we have a more and less substituted side of this alkene? No, they're equally substituted, so we wouldn't have any selectivity for getting the anti-Markovnikov product. Versus if we did our double bond here, do we have a more substituted side and a less substituted side? Yes. So this is going to be the one that you want to consider. This hydrogen is the one that was added with this OH. So for this, if we're doing syn addition, we need to draw them going syn. So putting an OH and an H. And for this one, the right side is the harder side. So let's start with the harder side. So let's imagine the OH is the red one over here, and it's going up and away from you. And we want it to go up in the plane, right? Then here, that originally is this hydrogen right here that's on a wedge. It's coming towards you. So when we rotate this, is that hydrogen still going towards you? Yeah, so it's on a wedge. It's just down now. And then that's going to force the ethyl to be on a dash over here. Okay? And then the left side's a little bit easier. Everything's just going to swap positions. So we want this hydrogen to be up in the plane. We want it to be all the way over here, which means the ethyl goes on the dash and the methyl goes over onto the wedge. So H goes up, the ethyl goes back on the dash, and then the methyl goes on the wedge. So now we have done the version where we've drawn the two things we added, syn, which is the correct stereochemistry of the reaction. The methyl and hydrogen are going to be cis to each other, and the two ethyls are going to be cis to each other. So our starting material was two ethyls cis to each other, a methyl, and a hydrogen. I hate it. Like, this is fully when I learned organic chemistry, I said, I'm not going to do that. Thank you so much. But it is like really testing, do you understand both the stereochemistry of the reaction and the stereochemistry of an alkene, which is why it's a great test question. But again, it's maximum 2 points, so I would say don't worry about it too much. You can always go back and rewatch part of like the section video to see kind of talking through it again. But with that, I'm afraid I need to press onward in order for us to get to the Wittig reaction at the very end. So we've talked about the simple alkene additions where we're doing all this detail work with mechanisms and stereochemistry. The complex ones do kind of cooler stuff, and we typically ask about the mechanisms a lot less. You're working much more at a line reaction level. So I'm going to talk about a few of them, not all of them. First up, we have ozonolysis. Ozonolysis takes a double bond and says, let me cut that. So it's really great at busting open rings. So if you ever go from a ring thing to a straight chain, ozonolysis is one of the first things that should come to mind. So the way I think about the Fick mechanism is ozonolysis, the first step, acts as like little oxygen scissors. It's going to cut the double bond in half, and then it's going to make it so that there's a carbonyl on both sides. So let's try it over here. If we cut it in half, I'm going to place a carbonyl on both sides. And then we have this kind of choice for our second step. We can either have DMS or H2O2. So DMS, dimethyl sulfide, is what we call reductive conditions. And so once we do our oxygen scissors, if we have DMS as the second step, we are done. There's nothing else to do. But if we are in oxidative conditions, we have H2O2, then we have to do one last step, which is if either of them were aldehydes, we have to oxidize it all the way to a carboxylic acid. So we're going to replace that H with an OH. So, given that, can you take like 45 seconds and try out the next two? And be warned that this is a reaction of alkenes, not arene rings. Arene rings react differently, which you're going to learn about in lecture 9. So it does not snip any of this, it only snips this. So for our second example here, we snip in the middle, make a carbonyl on either side. And if we do the DMS version, we are done. And so this is an aldehyde and a ketone. If we do the H2O2 oxidative version, our aldehyde goes all the way to a carboxylic acid here. For the last example, when we cut down the middle, it's going to form two ketones. And then with ketones, we can't take it further. So we're going to get the same products for both reductive conditions and oxidative because there's no aldehyde. Yeah.
Why don't you snip the
The
alkenes inside the ring?
Because she's not an alkene, she's an arene ring. She's a different functional group, so she does different reactions. And you'll learn the reactions of arene rings in lecture 9 tomorrow. Yeah.
So for the third one, since there's no aldehyde, that's why we're not making carboxylic.
Exactly. So if we were to turn one of these into a carboxylic acid, we'd have to break a carbon-carbon bond, which is very difficult.
Okay.
Yeah. Cool. So that's our little ozonolysis girl. Osmium tetroxide, I'll mention very briefly. So she is a way of making a vicinal diol where we have oxygens on adjacent carbons. Now, in lecture 7, you learned another way of making vicinal diols. How do we make this? Epoxides. So we could have had an epoxide. I'll just do it like that. And then we could have added like H3O plus. Or we could have had the flipped version and added OH minus. Either one would work. But the big thing about this one that we did in lecture 7 with an epoxide, epoxides make anti-vicinal diols. But osmium tetroxide makes syn-vicinal diols. It's kind of like a really like fine point, but it affects the reactivity. Because when the vicinal diols are on the same side, they can do fun and clever things. Like, I have a diol. I have a carbonyl and H+. Where have we seen that reaction before? What functional group does this make? Acetal! Oh my gosh, all the way back to lecture 3! Oh my goodness! So, syn-vicinal diols can make, like, go on to form acetals. And it's because the OHs are on the same plane. When they're on opposite planes, it makes it harder to form rings. And so, you're not going to see that as much. Yeah. It's a very common exam question of you make a vicinal diol and you have to see whether it's syn or anti to know which way you made it. So it's a great like line reaction question. You'll probably see some on practice exams. I wouldn't be surprised if it came up on the test. So that's why I like to flag it. Then the last one, epoxide formation with MCPBA. I just think she's neat. Like it's one of my favorite reactions in OChem 1 because she's a little quirky with this peroxide bond. She has one step with 4 arrows. She stands on business. She gets in and out and she's done. I just like it. So we have our second way of making epoxides. Halohydrin is the first way. MCPBA is the second way. I have no other comments on it. The other reactions I'm not going to really mention here. The radical, section 9, alkene reductions, H2, we kind of saw in the practice. And then the carbenoids, I just think they're kind of boring. So that's kind of the complex ones, but you're thinking much more at the line reaction level. You're thinking about disconnections and like drawing products. Last topic of the day, the Wittig reaction. So the Wittig is actually kind of one of the like most powerful reactions that you will see in this course because it is a new way of making carbon-carbon bonds. So far in this class, you've learned maybe 3 or 4 ways total to make a new carbon-carbon bond. You've done like organometallics. What other ones? I guess you've done like SN2 where cyanide, C attacks and makes a carbon-carbon bond. Any others? This may be your third way of making carbon-carbon single bonds. Double bonds, you've seen E1, E2. But this one's powerful because she makes a single bond and a double bond in the same go. So, the two things that come together to make our alkene, one side of the carbons comes from an aldehyde or a ketone, so some sort of carbonyl compound. And then the other side of the carbons comes from a new functional group called an ylide. Ylides are molecules that have a minus and a positive formal charge right adjacent to each other. So this one's specifically a phosphorus ylide. There are also like sulfur ylides that there are lots of ylides. But these come together and they are going to make an alkene. Notably, they're going to make a Z alkene over an E alkene. And we don't talk a lot about the why of that for this class. But one thing that you might kind of start to think about is Z alkenes are kind of cis alkenes. Those are the ones that are not as favored for making, right? And like normal like elimination reactions, we favor trans over cis. So if you see a Z alkene in a product, think more Wittig rather than elimination. Now, this is one of the only two reactions that you will learn to make an alkene. And then once you have an alkene, you can go on to all the different possibilities. So very powerful. The other thing is it can also make terminal alkenes, which was difficult to make via elimination. It was difficult to make via elimination because eliminations, we had Zaitsev's rule, where we always favored the internal alkanes. But this, if we think about our double bond as having two kind of carbon chunk areas, one of them's from a carbonyl, one of them's from the ylide here, you can easily make a terminal alkene by just making one of your chunks have only one carbon. So if you make the carbonyl have only one carbon, it's formaldehyde here. And that's how we can easily make a terminal alkene with this Wittig reaction. Or if you make the ylide your one carbon group, then that is what becomes the one carbon in the end here. So good at making the Z alkenes, which are harder to make in elimination, and also good at making terminal alkenes. Things to keep in mind. So now, the mechanism of the Wittig itself, I'm not going to go kind of beat by beat through it. Like the ylide's the nucleophile, it's going to attack the carbonyl. And then, this is the thing that's kind of cool. She's the boxy boy reaction. So she will form at one point this four-membered ring box, and then the box will just go boop, collapse, and then it'll click apart into two different molecules. And like that's just kind of fierce. I don't really have many other comments other than very satisfying. Love to see it. The other thing that we have to think about is we've never seen an ylide before, so we need to know how to make ylides. So ylides are made in a two-step process starting at an alkyl halide. The first step is we add PPH3, which is going to come in and do a backside attack. So one thing to note, if this alkyl halide was tertiary, is that going to be a good candidate for becoming an ylide? I see some nods no. Why? If this step is SN2, is it going to be a good candidate for becoming an ylide? No, because it's going to make it hard to do that backside attack. Then, once you've done the backside attack, you've installed the PPH3, she now has a positive charge. N-butyllithium is used just as a base to deprotonate it and give us our negative charge here. So that's how we get the negative and positive charge together and installed. So the thing that I think is going to be more useful to do than just go through the mechanism, this is a great mechanism question for tests. It's also great for synthesis. Like you 100% are going to see the Wittig once, if not twice, on the exam. Let's think instead about this kind of synthetic connection and disconnection of like, how do we just get the product without having to think through the whole mechanism complications? So I'm going to show you one, and then I'm going to have you do one. So the first one is you locate your alkene that you think was made via Wittig and chop it in half. Then we have two sides that we need to turn into our carbonyl and ylide. So we're going to get two options. So option number one, we could make the bottom part here, the carbonyl, and then the top part is just one carbon, right? So our ylide would be CH2, PPH3. That's option one for a combination, the bottom one being the carbonyl, the top one being the ylide. Or, option number two, we could make the top one our carbonyl, and the bottom one are illid. So now, if we have these options, which one's going to be better? Like, which one's going to be the better synthetic route? And to answer that, we have to think about forming illids. Which one's going to be easier to make, a secondary illid or a methyl illid? A methyl illid is going to be easier to make, and it's because to make an illid, you have to do an SN2 attack. And so if this is just a CH3 here, so much easier to attack than if this was on a ring. If it's on a ring, then it's going to be much harder to access, much slower. So our preferred combination is going to be these two together with our better illid. So this is less sterics on illid. So take a minute and try to do the disconnection here. And then once you've done that, try to connect these two molecules here. Mm-hmm.
So in this problem, do we get any stereochemistry?
You haven't so far. So we might just say ignore stereochemistry, but we could have a stereochemistry thing in it. Yeah. I'm not sure if you'll see any in the PEX exams or the rest of the problem set. It'll be consistent. So if you start to see some synthesis with stereochemistry, then yes, you have to account for stereochemistry. If not, then probably no. But we won't ask anything super crazy. Just 30 more seconds here. Y'all all have very different thinking faces. Some of y'all are peaceful. Some of y'all are like blank completely. Some look like frustrated. Some look like intrigued. Like lots of different thinking faces going on. So for this disconnection here, we cut in the middle. We make one side our carbonyl, one side the illid. So the carbonyl on either side, those are the easiest ones to draw. For the illid side, all we need to do is wherever the double bond was, we draw, like for this, a line to PPH3. So that's what it's over here. And then the carbon that was on the double bond is going to be the negative charge, and then PPH3 is going to be positive charged. Students often mess up a Wittig reaction on the line reaction by adding or subtracting a carbon, so just make sure your number of carbons is correct. Then the other option down here is you cut this off, and if you want to make this side the illid, you would put your PPH3 plus here, that's going to be minus. So we have this, and the other side's carbonyl. So here we have a primary illid, here we have a secondary illid. Which one's going to be better? Primary illid, because it's formed via SN2. So this is preferred. The very last one, where we are forming our product here, we know that we are going to get our carbon chunks from whatever is attached to the carbonyl and whatever is attached to the ylid. So on the ylid side, which I guess I'll do in kind of another color, green, it's going to be equal. So we're not going to have like an E or Z. This is going to be a neither orientation for our double bond. And then on our red side, one is going to be a methyl, and then the other one's going to be the base of the cyclopentane. So that is how we do a connection. And if we did have different versions, we want to form the Z. But that is all for today. Thank you for coming to section. Hopefully this was helpful in kind of putting some of the pieces together from lecture. I'll stick around for some questions. But I will see you in lecture. Have a good rest of your week. Yes. And for mid-semester meetings, remember it's going to be in the Smith campus.